Hello. Can everyone hear me?
Yes, sir.
Let's give a few minutes. Seems like more people want to get in. By the way, any questions on the homework problems that I assigned? Any particular questions you want to, that I can spend a few minutes before the class to talk about? Okay. When I look at the calendar, so here's my plan for the week. So we would finish 1.4 and start a little bit of 2.1 today. So my goal is to finish the majority of chapter 2 by this week. So for next week, maybe doing a little bit more on Monday or Tuesday, and maybe we can start a little bit of chapter 3 on next Tuesday. Then the exam probably would be on either Wednesday or Thursday. So tentative date for our exam 1 would be on next Wednesday or next Thursday. Let me see. So it would be either June 26th or June 17th. Any questions so far? All right.
Is the test going to be like the homework you gave us?
So last week we talked about our products and cross products. Okay, so these two product inputs two vectors, but that product returns a real value. Right? But cross products gives you another vectors in R3. So these two are from R3, and they return another vector in R3. They have certain algebraic properties that you can use, right? So so before the class, let's do a little quiz. So let's say you have a vector u in R3 is 2, -1, 0. Your v is 1, -1, 1. Your w is -2, -3, 1, 2. Something like that. All right, let's compute. U cross v plus w. right? Actually, U dot V cross W, and then the projection of U onto V. So this is the orthogonal of U onto V.
This is a quiz. Yes, no, maybe so.
And then the third thing is the equation of plane that covers these 3 points. All right, so for number 3, consider this is point A, point B, point C. So this is point A, point B, point C. So find the equation of a plane that contains point A, point B, and point C. Oh. I didn't hear any of you guys. Did any of you speak up before? Oh, I'm really sorry. Yes.
So for the first problem, should we do the dot product first and then the cross product, or should we do the cross product first and then the dot product?
So for the first one, right? Talk about first one. All right. So yes. The order is to do the cross product first and then do the dot products.
Okay, thank you. That's what I was doing. Just making sure.
Yeah, because the other way doesn't make sense, because the cross product will return you to another vector, right? And the dot product, you need 2 vectors to compute the dot product, right? So if you do the other way, if you like do the dot product individually, you will get numbers. You cannot do cross product on 2 numbers.
Thank you.
Is when is it due? Is this due during the class time?
You can I plan to let you guys do for 10 minutes, right? You can ask me any questions during this time, and then I will post the submission link tonight, and you can upload it by tomorrow. right? And then I would go over this quiz questions tomorrow at the class. So basically, you have tomorrow until noon to submit the quizzes. So for number 3, remember, if you have 3 points, right? You can construct 2 vectors that start at the same point. So for example, you can, if you want to start at point A, you can have vector AB, vector AC. Right? After you have 2 vectors, you compute the cross products. Remember, the cross product will be the one, the orthogonal vector on to the plane. After you have the orthogonal vector, then any vector will be orthogonal to that orthogonal vector.
right, Daddy? Oh.
Yeah.
I'm gonna just show it.
No, you could go for Monday.
No, I'm saying because how is she gonna pick me up if we're going to the morning session? And she doesn't have a car either.
Ray, I think you have not muted your mic.
Oh, my bad. My mic is not muted. I'm so sorry.
All right. So let's move on from this quiz. Again, I will post the lecture notes on Blackboard. You can always come back and revisit that, right? So today, we will finish up the last thing in chapter 1, which is the chapter 4 is about change of coordinates, right? And after that, we will have our beginning of chapter 2, which is chapter 2 is all about derivatives. We'll get to that later. So what is change of coordinates, all right? Remember in Cal 1, or even pre-calculus, you have encounter when you change your XY plane, all right, the Cartesian coordinate to polar coordinate system. So in that way, you can have certain functions will be easier to visualize. So for example, this is XY plane. When you have Cartesian between Cartesian and polar. So this is your XY. Every point will have your X coordinate and Y will be determined by both X coordinate and Y coordinates, right? And then for the polar coordinate system, it became it's determined by your radius and the angle theta. So I don't know what is the best way to draw this. Probably like this. Okay, so every point now is determined by the radius from the origin, r, and the angle from the x-axis theta here, theta. All right, and the relationship is determined by the formula x is equal to r cosine theta, and y is equals to r sine theta. Okay, so what is the benefit of doing this is that for let's say a function of a circle, right? In Cartesian coordinate system is the equation for this circle is x squared plus y squared equal to r squared, which is little implicit, all right? In order for you to get a relationship between x and y, you have to do a square root, and then you have to do it in sections, right? This section and this section, right? Because if you didn't separate into these two sections, it violates the vertical rule for being a function. Basically, right, for this point, you have two values, and that cannot be, a function cannot have two values on a single point. But for a polar system, this become much easier, right? So all the points would be just have a fixed radius with different theta. So the point would be just r theta, where the theta is just 0, 0 to 2 pi. That's much easier to visualize and much easier to sum it up. Okay. So now we are doing, similar things on three-dimensional Euclidean spaces as well. So in R3, the Cartesian products or Cartesian coordinates is x and y and z, right? They're the standard basis is I and j and k. They represent a unit vector in the x, y, and z coordinates respectively. Okay. If we want to change your coordinate system, what other coordinate system do we have in R3? So one of the option is called cylindrical coordinate system. Right. In this case, all right, we are keeping the coordinate z, and then we represent or we change x and y coordinates into coordinates like a polar coordinate system, so r and theta, right? So basically, in cylindrical coordinate system, your x is the x in the Cartesian is represented by r cosine theta. Y is r sine theta, and your z is the same as the z at in the Cartesian product, Cartesian coordinate system. So the r here is in the cylindrical. These are cylindrical. Or these red arrows. And the x and y and z are Cartesian. Okay. So this is the formula, or like the method on change of coordinate system between Cartesian and cylindrical. So a visual representation for this is that we are grouping points why is it called a cylindrical coordinate system is that it best illustrates points at the in the cylinder in R3. All right. So for you to represent the points in the cylinder, all right, it would be kind of hard for a Cartesian products because you have to separate it into a cross section of circles, and each circle, like in XY plane, you have to use a implicit formula, x squared plus y squared equal to r squared, right? But for cylindrical coordinates, you don't have that sort of problem because for a fixed z coordinates, the point is like a circle, which is easier to represent it in a polar coordinate form, right? Because they have to fix r, and then you just change the theta. You vary the theta from 0 to 2 pi. So this is the collection of points r theta z, where you fix your r, right? And then your z is from, let's say you have height from A to B, and then your theta is from 0 to 2 pi. So that's one of the advantage of using cylindrical coordinates is when you have when you encounter a scenario that you can sort of how do I say it? Is sort of your z coordinates is kind of independent of x and y, and then your x and y is better represented by a polar coordinate system, right? So you can think of a cylindrical coordinate system is a polar coordinates with a z-axis. So whenever you have a scenario when you can better represent your functions or your points with the polar system, right? You can just use your cylindrical coordinate system. Right. Another one of the coordinate system is called spherical. Coordinate system. Okay. So for spherical coordinate system, your x and y and z or three coordinates will be transferred to another one. Okay. And to better visualize the spherical coordinates, let's start with a sphere in R3. Imagine this is a sphere. And right. How do we represent point on the sphere, right? Other than usually usual x, y, z. So what are the other ways to recognize these points? Okay, so another way to visualize the points on the sphere is by first knowing what's the distance between the point and the coordinates. Okay, we call that phi. So this is a distance from the point to the origin. Okay. So after you fix your phi, you fix the particular sphere you're on. And then now you're on the surface of the sphere. Let's say, for example, like, let's use the Earth, all right? That would be one of the familiar objects that are spheres. Right? So imagine you're on a particular point in on the Earth, right? How do we locate you, right? All right. What you can the location is determined, can be determined by two angles, right? So first is the angle from the z-axis. This let's call that what does the book use? God. Phi and theta. Okay, phi and theta. So let's call this phi. So phi is the angle between the vector and the z-axis.
What letter is that, Professor?
I'm sorry?
What letter is it?
This letter phi.
Oh, phi. Thank you.
Okay, phi, like a Greek alphabet, right? And with these two is still not enough information, because you're just fixing the points around this, let's say, latitude. Okay, so for example, if you think of the equator as the one on the equator is on the XY plane, right? And when you fix when you fix your phi and your rho, you're only fixing the latitude. For example, let's say if Beijing and New York has the same latitude, right? So these 2 points will have the same phi and rho, but these 2 points are not the same place, right? So if you, let's say, if you your laws, you only tells the the people your phi and your rho, right? They don't know like what specific location you're on. So you need one more information to distinguish the points. Right? The last one is the angle theta. Choose this color, right? Your theta. So what is theta? Is that when you project your points on the XY plane, okay, the angle between the point, the vector and the x-axis. So phi is the angle of the projection on between, sorry. Projection on the XY plane. And the x-axis. So why do we choose a system like this? All right. What are the connections? So let's observe that, you know, when you only look at x and xy plane, all right, the this green arrow, okay, when you look at the geometry of this triangle, right, because this is a projection, this is a normal vector, so this is a right triangle. So this, let's, you know, put this triangle on a plane so that would be better to visualize. So this is the points XYZ, or we are represented by phi, a rho, phi, and theta. This part is the vector, the actual vector, and here is the projection. The angle is phi. Actually, the phi is, no, the phi is on here, right? Because this normal vector is parallel to the z-axis. So the phi angle measures between the vector and the z-axis, right? So these two are parallel, so these two angles are the same, right? Anyone see that? So let's say you have a z-axis here. This is your phi. Because these two are parallel, these two angles are the same. Right. So now this vector has the length the same as the remember the phi. This edge is the opposite of the angle phi. Opposite over hypotenuse is sine. So you know that let's say this edge has the length r. R is equals to rho times sine phi. Okay. And then this length is exactly the length of the z coordinates, right? Because we're projecting onto the xy plane. So this is exactly the length of the z-axis, z coordinate. So you know z is equals to rho cosine phi. That works on the when you have a negative z, because in that case your phi would be more than 90 degrees, and that becomes a negative. Okay. So now we have your vector r like this. Now with the r and theta, this becomes the polar coordinates. So x is equals to r cosine theta. Well, you can just replace r by using rho and psi. So this is rho sine phi cosine theta. And y is equal to r sine theta, which is rho cosine sine phi sine theta. Okay. So the idea is that r and theta is the same as the polar coordinates. So now we have a formula converting x, y, z, or between x, y, z and rho, phi, and theta. Okay. Why is this important? Is that well, later on when we do chapter 5, well, that the chapter on integrations, okay, certain functions are a little bit more complicated when you integrate it on Cartesian coordinates. However, when you change your coordinate system, it will be much easier to integrate, right? For example, let's say when you want to find the volume of the ball of certain like radius, okay, is much more complicated to represent the points of this ball using Cartesian coordinates system. The best way of representing the points using Cartesian coordinates is to use an implicit formula, x squared plus y squared plus z squared, y squared plus z squared less than or equal to certain radius r. Okay. And it's really hard to come up with an integration formula on, using these coordinates x, y, and z. However, it would be much easier to use spherical coordinate system. That's why it gets the name of spherical coordinate system. We mimic the way of representing points on the sphere, and then we use this way to represent the point in the three-dimensional Euclidean spaces. Basically, we visualize the point, we group the points with the same radius, and then we change the angle phi and theta to represent a point on the sphere. Okay. Okay. All right. Any questions so far? Okay. Let's do some examples before we move on. So let's say you have your points in through R3 represented by Cartesian coordinates 3, -1, 2. Right. How do we represent these points in cylindrical coordinate system? Okay. So first, we know that x is equals to r sine cosine. Y is equal to r sine theta. And z is equal to the z. Well, the z here is in the Cartesian. And the z on the right-hand side in the cylindrical. But there are two, these two are the same. So you just like copy and paste. How do we determine r and theta? You do the similar things in polar coordinates. Okay. So observe that x over y is equal to cosine. Let's do the other way. Y over x equals to sine theta over cosine theta. if your x is not equal to 0. Right. On the other hand, if x equal to 0, that means our cosine theta is equal to 0. Well, either r is equal to 0. So in that case, we fix theta to 0. Or cosine theta is equal to 0. That means theta is equal to pi over 2. Or theta is equal to, what are the other one is 3 pi over 2. Okay. And then to further distinguish these two, we use the y coordinates. All right, if y is positive, that means you have pi over 2. If y is negative, you have 3 pi over 2. So let's bring down the unit circle. So this is theta is equal to 0. This is theta equals to pi over 2. Theta equals to 3 pi, and then this is theta equals to 3 pi over 2. Okay. So remember the in a unit circle, your x represents cosine of theta, and then your y is represents sine of theta. So cosine theta is equal to 0. That means you have x equal to 0. So it's either this point or that point. Right. In this point, you have positive y value, so you have positive sine. In here, you have negative y value, so you have negative sine. So let's see, this one, if your sine theta is greater than 0, and here is if sine theta is less than 0. Okay, so this is the special case when you have x equal to 0. So only this point, 2 points, or the origins, right? So if x is not 0, so we definitely have not non-zero radius r and non-zero cosine theta. So definitely other points here. So now we can do y over x. And remember, sine theta over cosine theta is tangent of theta. Okay. So now you can do the inverse sine of tangent y over x. All right. However, inverse of tangent only gives you angle between pi over 2, negative pi over 2 and pi over 2. So it's either here or here. So this theta can be either here or here. Or how do we know which part of the unit circle it belongs to? Is determined by your x, right? If you have a positive x, it's definitely here. So it's between pi over 2 and negative pi over 2. So if your x is greater than 0, that means your theta is between pi over 2 and negative pi over 2. So you can just use your inverse of tangent. However, if x is less than 0, that means it's this part. Okay, so this part is when you have theta is between pi over 2 and 3 pi over 2. So theta is between 3 pi over 2 and pi over 2. So that means theta is tangent of the inverse tangent, but you have thrown in the theta, I mean pi. Right. So let's see how we can convert, I mean use it in the actual example. So now you have 3 minus 1 and 2. Now we want to represent it in r, theta, and z. Okay, your z is the same thing as the z in the Cartesian. So this is 2. Right, so for 3 minus 1, let's look at the circle that contains 3 and minus 1. Minus 1 somewhere here. Okay, so what is the radius? R is square root of x squared plus y squared. The square root of 9 plus 1 is 2 radical, sorry, it's radical 10. So when you divide, how do we determine your theta? Is that now you have non-negative x, and it's on this part of the circle. That means your theta is between negative pi over 2 and pi over 2. So we can directly use the inverse tangent of y over x. So inverse tangent of minus 1 over 3. What's the answer?
Professor, what's that under the r over there on the right side? That's the square root of 0 or square root of 10. What is that?
Square root of 10.
Square root of 10. How did you find that?
I remember you have x squared plus y squared is equal to r squared, right? Similar to the polar coordinate system.
Right.
Right. You just treat x and y as your x and y in the xy plane, and then you change that to the polar coordinates. Is that good?
Yeah, I got it.
So determine the theta may be a little bit tricky, but you get the idea. You look at the angle. You look at the angle theta, and then you find the value by look at the inverse, the inverse tangent of y over x, and then depending on what x coordinates, what sign of x coordinate is, you have to add a pi or not. In this case, you don't have to add the pi because it's already, it's already in this part of the circle. So this part, the tangent theta is 1 over x, and on the other side, tangent theta.
My math degree, so I got to get certified to become a teacher, math teacher. Right?
Also y over x. So yeah. So and then you because inverse tangent only gives you this part. So for this part, you have to add a pi to make it even. So this point and that point have the same tangent value. But when you do the inverse tangent of y over x, it all gives you to this point. So this point and that point have the same tangent value. So when you do the inverse tangent of y over x, this 2 point all comes down to here. So in order to, distinguish the theta, these two theta are different. Right? The other theta on this side, in this part of the circle, you have to add a pi. So, yeah. So in this case, you don't have to add the pi, so you just, this tangent, inverse tangent of 1 minus 1 over 3, and then is some angle, I don't know. Can someone do the calculation for me?
Jersey, it'd be crazy on 272 though.
Arctang of minus 1.
Wrong.
It's
Running in bad, man. Walking on the street like it's
minus 18.43 degree, something like that.
Oh, look, that nigga will move.
Right. If you use a radian, let's see, minus 1.
What's that?
So minus 0.3217 radian. Is that correct? Does anyone do the math as well?
How did you find that?
This is the arctangent, right?
Yes, I know that. I see the tangent. How did you find the negative 0.321? What is that? It's too small for me.
Yeah, plug it in the calculator. Probably this is not a good example. Let's do 2. It will be much easier, I think. Okay, so this case is 2 squared plus minus 1 squared. So it's 4 plus 1 is radical 5. And then now you have minus 1 over 2 is arctangent of 1 over 2. Minus 1 over 2 is minus pi over 4. If you guys remember from the unit circle table, this is one of the special angles. This is minus 4. So far, so good. Okay, so now we finish our business in cylindrical coordinates. How do we do it in? Let's change that to spherical coordinates. Okay, so the easiest one, the easiest coordinate to determine is the phi. That is the radius between the point and the origin. This is the square root of x squared plus y squared plus z squared. So the square root of 2 squared plus minus 1 square plus 2 square is square root of 414. 9 is 3. All right. So now it comes down to finding your R and theta, okay, or phi and theta. So how do we determine the first the phi? Right. Remember, your phi is equals to the angle between the vector let's say this is your vector and your z-axis. So this is the phi angle. So so now we can use the formula about the property about in the product is that this is the z, well, the vector on the z-axis is the standard basis k dotted with x, y, and z divided by the length of k and the length of your x, y, and z. Well, the length of k is just 1. That's the standard basis. And the length of x, y, and z, we know that is phi. So this is k dot x, y, and z divided by 1 times rho. Well, k is, remember, it's just 0, 0, 1. So when you do the dot product on top, it becomes z, and on the denominator is rho. So cosine phi is z over rho, because the angle between the vector and the z-axis is strictly between 0 and pi. So the arc cosine makes sense in this case. Phi is equal to the arc cosine of z over rho. Right. And how do we determine theta? Right. We do the same thing as, you know, polar coordinates. So now we have x and y, we convert it into r and theta. So in this case, only in this case, your r is given by the formula rho sine phi. So after you find the phi, you put it into the sine, and then you're done. Well, you have to put the absolute value because the sine phi can be negative. I don't think, well, hold on. I don't think the phi can be any negative because phi is between 0 and pi, and then on that interval, the sine value is always positive. So, yeah. Okay. So another way to write this is, you know, because cosine phi is z over rho, this is rho of, we can represent sine phi as radical of 1 over cosine square. So rho of square root of 1 minus z square rho square. And then you can put the rho back, rho inside the square roots. It become rho square minus z square. Either way, you would get the in this case you definitely have to put well, you don't have to, because your rho is strictly greater than or equal to z because of the triangular inequality. So this one is fine as well. So far, so good.
I didn't understand what you did there, Professor. If you could go back.
So in order to determine the theta, you is similar things with as we do it here, right? If we have x and y, you will have your theta and r, right? Except in this case, your r is determined by rho and phi.
How did you find phi in that equation then?
So how do we find phi? Is when you look at the vector, right, this is the origin.
Oh, that's the formula right there to the top right, the K formula.
Yeah, because if this is the vector and this is the z-axis, the angle between the vector and the z-axis can be related by the dot products. So that's the property of the dot product. The angle is the dot product divided by the length of each vector. Right. So we picked the standard basis as the vector on the z-axis. So that's the k. Remember, standard basis has length 1, so that's why the length is 1. The length of the vector between 0 and xyz, right? This vector had the length phi, had the length rho. So we're dividing rho here. This is rho. This is 1. Right. So the top is the dot product between 0, 0, 1 and xyz. Well, when you do the dot product is x times 0 plus y plus times 0 plus z times 1. So only z is left. So that's why cosine of phi is z over rho. Right? Because the angle phi is strictly between 0 and pi, we can directly use the arc cosine to find the exact value of phi. But oftentimes, we don't need to have the concrete value of phi, because the important information is the cosine of phi and sine of phi. For example, why sine of phi is important is that you can, after you know what the sine phi is, you know what the r is, and then you can use the r to determine theta, similar to what we did before, like a polar coordinate system. Okay. So in this case, your theta is negative power 4. If you do the same thing like here before, the arctangent of y over x. So theta is minus power 4, and then your cosine of phi is z is 2, rho is 3, so it's 2 over 3. Inverse cosine of 2 over 3, I don't know. (0.841), something like that, if you plug in the calculator.
So you're replacing the XYZ coordinates with what we had before. It's not just, you're not leaving it at XYZ.
So remember the XYZ is 2 minus 1 and 2. 2, negative 1 and 2.
I got it. That's what confused me. I'm like, I didn't see you replace the variables. So I got it now.
Yeah. So yeah.
I thought the final product was the square root of P minus Z. I'm like, why didn't you use the
no
value? But I see it now.
Well, first of all, this is rho. Rho is
you're just showing.
Yeah.
Yeah, sorry about that. Rho.
Yeah.
I gotta get the Greek out there, right?
Yeah. Because we're using Greek letters to represent the spherical coordinates. So that's one way to distinguish Cartesian and polar, or Cartesian and cylindrical, or Cartesian and spherical. So now your x and y and z becomes rho, phi, and theta. So rho, phi, and theta. So far, so good?
Yes, there's a question in the chat. Someone asked.
How do you get, well, K is, remember that it's standard basis, right? That is the standard basis on the z-axis. We pick that vector to compute the angle between the z-axis and the vector. Because phi, as by the definition, is the angle between the vector and the z-axis. Good? Okay. So now let's move on to, we still have about 1 hour. I think that's enough of time. Chapter 2.1. Graphs of functions. So in calculus 1 or pre-cal or whatever, we only talk about functions on xy plane. Right? So because the reason is because when you have y equal to fx, the graph is a curve on xy plane. So for single variable functions, however, for multivariable functions, let's say f, you're mapping a point in Rn, right? Because you're using n variables. and then you map it to a value R, like a real value. So you assign f of x1, f of x2, dot f of xn as a number. Let's say this is your y. Okay, what does the graph of this function look like, right? And it's hard to come up with the function altogether, right? However, it's much easier to cut it down, cut this function into pieces, right? How do we do that? Is we introduce a concept called level sets. Right. So for a fixed value, C, fixed real value, right? Now we'll only look at the points such that in Rn, such that your f of x1, x2, xn, the function returns to this given fixed value C. All right, we only look at the points of this. In other words, we only look at the points that give you that such that the functions gives you the value C. They all have the same output C. Okay. Because, well, this is a result from topology, but it is actually very intuitive, right? Because your value C is a close point in the real line. So that means your input here, because your function f is continuous, that means your level set must be a closed curve or closed surface in Rn, because it's a closed subset. So one of the property is that this level set is a closed subset in Rn. Well, let's begin with, well, let's specifically. If you have a level set, when your function is mapping R2 to R, that means your function only takes two variables. Right. So the level set has a special name. Is called a level curve. In R2. And when you have function map from R3 to R, so that means you take three variables. Right. This level set is called level surface in R3. How do we visualize it? So let's take the example in R2. So for example, if you're familiar with geography, is that to have a map or three-dimensional map of a mountain, all right, is much easier. Well, when you have a map, let's say this is a map of a Pocono mountain. When you have a position here, you don't know how high that position is in altitude. Right? You don't know whether or not you're on the top of the mountain or on the bottom of the mountain, right? So the map, the helpful information for you is to draw, is to group the points where you have the same height. So that means along with this line, let's say they are all 1,000 feet tall, or 1,000 feet high. And then when you move closer, it becomes higher. And this is, let's say 1,200 feet tall. And then you get closer and closer, and then suppose there are like 2 peaks here. Then this 2 will have 1,400 feet. Oops. Okay. So this is what we call a level curve. Is that they have the, if our function is the height function for a given point, is the height for a given point x, y, right? This is a function that takes 2 values and returns a real value. Height is the real value. So the level sets for the function h would be a collection of these level curves. So for example, when you have a level curve of 1,000 feet, right, this is the collection of points that are 1,000 feet tall. When you step on this point, you know you're 1,000 feet from the sea level. Right? And then when you move on to another level curve, you change the height. So for example, when you travel from here to here, now you're on the points where you are 1,200 feet from the sea level. And then you move on and you move on. These 2 level sets are representing the points that are 1,400 feet tall from the sea, height from the sea level. All right. And then I'm only picking 3 level curves here, but you can imagine there are infinitely many level curves in between here, 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 and so that it fills the gaps between here and here. The level curves, because level curves, the fixed value c, you can take any real values. So it could be 1,000, 1,000.1, 1,100. 1,100, 1,100.333, something like that, so that the level curves fills up here. All points in XY plane can fit into, at least one set of one of the level curves here, right? And then when you put this level curves in the corresponding z value, so now in R3, you can represent this mountain, the Pocono mountain, in a 3-dimensional Euclidean spaces. So for example, this is 1,000 feet. And then when you move on to 1,200, it becomes taller. And 1,400 becomes even taller. Okay. And imagine the other level curves fills up between these two gaps. So it goes from this mountain to this mountain and then goes down here. Then the other way as well. So you have a picture of a mountain. Okay. It's really hard to visualize it. Let me see if the book has a better example. Right. So let's see, you have something like this. Okay. So in this case, this is part of the level curve, one of the level curve. Let's say x plus y is equal to 150. And then this one is another level curve. Let's say this is the level curve of h is 200, something like that. Right? And then when you collect all these level curves and then put it into a corresponding z-value, I put this level curve as in the z equals to 200. And then do the same thing for the 150 level curves, 100 level curves, so on and so forth. And then when you put these level curves together and then you fill up all the gaps, right, the curves become a closed surface. So that's why the general picture for the graph of H, right, is a closed surface in R3 because you represent you represent it in 3 coordinates, right? X and Y, and H of X and Y. So the collection of X and Y and H of X and Y, right, will look something like this. So far, so good? All right. So this represents the point H, X and Y, and H of X, Y. Okay. This is what we call the graph of similar to the idea in Cal 1 when you represent the function y equals function of f of x by by the point x f of x. So now you because you're using 2 variables, you put x and y, and then you put the value of h into the z coordinates. Or you can do the same thing for three variable functions, except in this case, it's really hard to visualize the graph of f because the graph of f lies in the R4. So in this case, the graph of f is the point x, y, and z, and then f of x, y, and z. This is in R4. Is no easy way to visualize a four-dimensional Euclidean spaces. You can't visualize what the graph looks like. However, what you can do is to look at the levels surface. Okay, and see what this level surface look like in three-dimensional spaces. So you would have some idea on how the graph look like. So for example, say you have f of x and z is equal to x squared plus y squared z squared. So the level surface for f equals to, let's say, 1. Is the same as you look at the points such as x squared plus y squared plus z squared equals to 1. This is precisely the point in the unit sphere. Okay. And then you do the same thing for f equals to 4 or 9, and then now you get another sphere. Okay. So now the level surface is basically all the spheres in R3, right? Sphere of radius 1, 2, 3, 4, 5, etc., etc., etc. These form a level surface for this function f. All right. And then if you can imagine the graph of this f is basically gluing all this surface in R4. I don't know how it looked like, but basically you glue all this sphere in together and then it becomes the graph of f. And any questions so far? So why the level sets are important is that, you know, when you go from one point in the level set to another point in the level set, you didn't change the value of f at all. So for example, in this case, when you fix a level set here, right? You fix this sphere. When you walk along this sphere, this f doesn't change your value at all. So one of the example is, for example, in physics, right? Your gravitational force on the Earth only depends on the heights, right? The higher you go, the less gravitational force you have. Right? So if you represent the amount of force by the function f, some sort of like a minus something m over, I forgot what's the formula, but is related to the height only. So it's something of g of square root of x squared plus y squared plus c squared, something like that, right? So as you can see that when you walk along the earth on the same height, right? So for example, you walk on the ground, you experience the same amount of force everywhere you walk. So that's why when you have a very smooth surface, flat surface, right? You don't need to well, when you push a ball on this ground, right, it will just roll on themselves because because the force is the same everywhere. The gravitational force doesn't do any work on this ball, so the ball would not stop by itself. You just like roll around this smooth surface, right, until the friction puts it into complete stop. So that is the one of the property that the level surface have. Let's do another example in the book. All right, so let's look at question number 3. Okay. So now we look at the level curves for f when the value is of f equals to 0. So this is the same as the point xy such that x squared plus minus y squared equals to 0. So that's the definition of f. All right. So it's the same as saying that x squared equals to y squared. So the saying is that the absolute value of x equal to absolute value of y. So the only graph that satisfies this is the graph 3. So this is oops. So this is the graph of f, the level curve for f of xy equal to 0. So let's look at the graph of this color, f of xy equals to 1. All right, so this is the same as saying this space, right? F x y equals to 1, same as saying x squared minus y squared equals to 1. This is the same as saying that y squared equals to x squared minus 1. And then so you know that because y squared has to be a non-negative number, that means that when x is from 0 to 1, this is inclusive. 0 to 1, x squared minus 1 is less than or equal to 0, right? And then since y squared cannot be less than or equal to 0, that means y is not defined on this region. So you look at the graph such that there's an empty gap between when actually it's -1 to 1 as well. We can expand. You can do the same thing for when x is negative. So you look at the graph such that it has the gap between -1 and 1 for x-axis, and that is here. We talked about. So that means that this is the level curve for f equals to 1. So far, so good. Same thing when you look at the level curve for f equals to -1. This is the same as saying y squared equals to x squared plus 1. Right. Similar idea you can apply is that when x goes, when y squared is equal to x squared plus 1, right? The range of y, well, actually y squared is strictly greater than or equal to 1. So that means that the absolute value of y is also has to be greater than or equal to 1. So you look at the graph such that there is a gap between 1 and -1 for y, right? This is empty because the range forces it to be greater or equal to 1. So that means there is a gap between -1 and 1 for y. So that's why this is the level curve for f. That's y equals to -1. Any questions on this material so far? Okay, so that's everything I want to cover for today. Tomorrow we will start talking about continuity and limits. And to give you a little bit idea on chapter 2 is we would like the ultimate goal is to, for a function, a real value function, f of x1, x2, xn, right? We want to have an analogous idea from the derivative in f count 1 to here. So for a real value function f, we want to find the derivative. So we want to define the concept of derivative in this real value function f. But before we talk about derivative, we need to first clarify what points are able to be derivative, to have a derivative. So the points where derivative are defined. Okay. And then before we talk about how do we define derivatives, we need to define the concept of a limit and continuity in Rn. So similar to Cal 1, you start with limits, and then you talk about the derivatives in this graph by talking about whether or not the limit makes sense. So in Cal 1, the limit, the derivative makes sense if this limit makes sense. But how do we have an analogy between this definition of derivative and the function, the real value function in Rn, right? Because the numerator still makes sense. This is a real value, this is a real value. But what is the h? You can't divide a vector. We only talk about numbers. And how does the limit make sense in this case? The limit doesn't make sense at all. All right. So this is what the main goal of this chapter. I hope this can help you have a bigger picture on what this chapter is talking about. Okay. So I guess that's it for today. Any questions? I guess I will see you guys.
Yes, I actually have a question.
Yes.
I have a question. I was looking at the homework and I was wondering if you could just go over one problem of the homework.
Which one?
It's going to be chapter 1.1. I was having an issue on 17.
Which section again? 1 point.
Chapter 1.
1.1?
Correct. The line passing through -1, -1, and 1, -1, 2.
This one? Or this one?
I can't see it, just see your screen.
Oh. Sorry, I thought I'm still sharing the screen, sorry. I think it's this one, right?
17?
17. 17, so this one.
Yes.
All right, so so you want the line to pass point -1, -1, -1. And
1, -1,
2.
and 2.
Right.
Yeah.
So if the line pass these 2 points, one thing you know is that it's parallel to the vector that connects these 2 points, right? So you have -1, -1, and -1. Another point, 1, -1, and 2. You can easily find the vector connect these 2 points, right? Let's say this is P, this is Q. What is the vector PQ?
Two, 2,03.
So is can you expand the process? How do you
Yes.
take it? Yeah.
So it is Q minus P.
Minus P. So that is 1 minus 1, 2 minus 1 minus 1 minus 1, right?
Yes, that's correct. And
Okay.
then that is equal to 2, 0, 3.
3. Yes, that's correct. Right. So now you know the line is parallel to this vector. Right. So you know the L has the point parallel to the vector. So let's say the vector is origin here. This is the vector PQ. When you span this vector PQ, right, you get a parallel line that contains the origin. Right, this is when you span the vector PQ, you get a straight line that such that the origin is on it and is parallel to the line that contains PQ. So these two are parallel lines. So this is the first step. You span the vector PQ. However, this doesn't give you the actual line. One of the thing you miss, the blue line is missing, is that it doesn't contain either P or Q. However, we can always fix that, is that, well, if this is your alpha V, and this is your vector P, when you add these two vectors, this is the parallelogram, you get to the diagonal point of this parallelogram, which is a point lies actually on the line PQ. Right? And then we can do this for any span of V as you want. Shouldn't use V, I should use PQ. So the for any span of alpha PQ, you get another set of parallelogram, and then it maps you to another point of the diagonal, which is still on the line PQ. So when you do this for all alpha PQ, you get this process will return you to all the points in PQ, and that's exactly how you represent the points in this line. So L is equals to the set such that is alpha times 203 plus P, which is minus 1 minus 1 minus 1. But when you simplify this, this is 2 alpha minus 1, 0 alpha minus 1, and 3 alpha minus 1. Does that make sense?
Yes, that makes sense.
Good. All right. Okay. Remember to submit the quiz by tomorrow noon, and then we'll go over the quiz tomorrow. And I guess I will see you guys tomorrow.
All right. Thank you, Professor. Take care.
Take care, Professor.
Yeah.
Thank you. Have a good day.